Thank you very much, Mr. Chairman, for the kind introduction. And I would like to thank the organizers of this scientific forum for having invited me on the occasion of 50th anniversary China-Austria diplomatic relations. A few words about the outline of my talk. I'll begin with saying a few words about the building of the immersed tunnel connecting the two parts of the Hongkong-Zhuhai-Macao Bridge, abbreviated as HCMB. Then I'll report on two sub-projects of the joint Austro-Chinese project, bridging the gap by means of multiscale structural analysis. A couple of brief comments on the witnessed development of modern China for almost 40 years. This slide, ladies and gentlemen, shows the course of the HCMB bridge connecting the two parts of the bridge. To the right, you see Hong Kong, to the left, Zhuhai. You see here the tunnel between two artificial islands. And the two parts of the bridge are connected by a road tunnel with 3 tracks in each direction. The tunnel is embedded in a trench. So what you see here is the East Artificial Island. It's one of the 2 inlet structures into the tunnel at the seabed. I'm coming now to, sorry, it doesn't function well. I'm coming now to the
Professor Mang, I'm sure.
The tunnel consists of 33 elements. The length of an element is about 180 meters. An element consists of 8 segments, hence the length of a segment is 22.5 meters. At first, the elements 1 to 29 are installed from the left to the right, and this is followed by the elements 33 to 30 from the right to the left. Finally, the gap between elements 29 and 30 is closed by a special segment of 12-meter length. Ladies and gentlemen, let me now say a few words about the production of the tunnel segments in a factory on Niu Island. The left figure shows the reinforcement of a tunnel segment, and the right one refers to placing of the concrete. The dimensions of the cross sections are truly huge. The width is about 38 meters and the height about 1150 meters. This slide shows the factory for production of the tunnel segments, and it's about here. Then you see the place of assembling of the tunnel segments to the element, the pool, and the gate to the sea. Let me say a few words about the preparation of the transport into the Chinese Sea. After hardening of the segments are assembled to elements with the help of pre-stressing cables. Then the elements are sealed in order to float them from the place of production to the position of the installation. The gate is then closed and the pool is filled with water in order to enable swimming of the elements. Then the gate is opened to allow for outflow of the water into the sea until the water level in the pool has sank to the level of the sea. Here you see the exit of a tunnel element with the help of pontoons from the pool. You see the green path pontoon into the South China Sea. The distance to the building site is approximately 12 kilometers. Now you see that the swimming tunnel element reaches the building site. You can see it here in the background. A few words now about the installation of a tunnel element. It's a challenging task because of the following reasons. First, a tunnel element is nearly twice as long as a soccer field. The largest immersion of the tunnel elements is approximately 50 meters. The length of the tunnel is approximately 5.6 kilometers, And heavy seas make the installation of the tunnel elements more difficult. Now, a few comments on the process of immersion of the tunnel elements. By means of fluting of the containers, you can see them here, inside the sealed tunnel element, the latter is immersed. The process of immersion is controlled from the pontoons with the help of ropes. The sketches at the side of the figure refer to the production of a waterproof joint between two neighboring elements. Well, let's have a look at the uppermost figure. By means of hydraulic joints, the immersed tunnel element is pulled to the precedingly installed element until full contact along a special sealing element is reached. Then the sealing element results in a water-filled reservoir between the two bulkheads, the vertical parts of steel. The water is then pumped out of the reservoir. The water pressure at the other end of the new element creates pressure on the sealing element. It results in sealing of the joint between the new and the precedingly installed element. The bulkheads are then removed and a second sealing element is installed in the pumped out region in the interior of the tunnel, resulting in a forced closed point. This shows the backfill of the immersed tunnel with gravel. Finally, a segment of 12 meters length is brought in for closing the gap between the elements 29 and 30. The opening of the Hongkong-Zhuhai-Macao Bridge by President Xi Jinping took place in a ceremony in Zhuhai province, Guangdong, on October 23, 2018. This slide gives you a view at the completed Hongkong-Zhuhai-Macao Bridge. The bridge was opened for public transport on October 24, 2018. Ladies and gentlemen, let me now turn to a joint Austro-Chinese basic research project accompanying the erection of the HCMB. The title of the research project reads as Bridging the Gap by means of Multiscale Structural Analysis. The time period of this project ranged from 2015 to 2020. It was financially supported by the Austrian Science Fund and the China Scholarship Board. The aim of this project was an assessment of the added value of multiscale analysis of tunnel linings. Research partners were the Geotechnical Department of the College of Civil Engineering of Tongji University, cooperating with the Institute for Mechanics of Materials and Structures of the Technical University of Vienna since 2005. Let me now turn about an important analysis tool. I'm sorry I cannot save you completely from a bit of mathematics, but I'll try to keep it as simple as possible. Multiscale analysis for prognosis of the load carrying capacity of structures. What are such analyses about? Despite their macroscopically homogeneous appearance, many building materials have an inhomogeneous microstructure. They contain several constituents that can be distinguished at a sufficiently small length scale. Multiscale analysis enables quantification of the influence of the microstructure on the macroscopic behavior of such materials. What is the practical significance of such analysis? Well, they enable realistic mathematical description of the material behavior. Since the collapse of structures is often caused by material failure, the quality of prognosis of possible collapse scenarios strongly depends on the quality of these mathematical descriptions. Where does the knowledge about such scenarios come from? In order to prevent possible failures in civil engineering, or rather keep the damage caused by unforeseeable catastrophes for mass, structure, and environment as small as possible, research in structural mechanics is dealing intensively with the failure of structural elements and connected with it with the collapse of structures. I'm the following presenting two examples to this. The first example refers to the material reinforced concrete. It shows the collapse of 3 cooling towers of 114 meters each, made of reinforced concrete. This happened in England in 1956, during a hurricane force storm. The left figure shows the collapse of the cooling tower, and the right one illustrates the situation after the collapse of 3 cooling towers. The second example refers to the material wood. What is shown is the collapse of a wooden ice rink in Bad Reichenhall, Germany, in early January 2006. The main reason of this collapse was degradation of the wood-to-wood adhesive bonded joint caused by moisture of the ice rink. Ladies and gentlemen, a few comments on the nature of multiscale analysis for prognosis of the load-carrying capacity of structures. Experimental simulations of the failure of building construction are often technically and or financially unfeasible. Multiscale analysis in the framework of the finite element method, that is a well-established and very powerful numerical method, a frequently useful alternative. A prominent role in these analyses are so-called homogenization techniques. They are an important ingredient of multiscale analysis of material parameters. Let me explain this by means of the figure shown on that slide. The gray part illustrates schematically a structure. Its characteristic length is denoted as uppercase L, and the stretch of the load is denoted as uppercase lambda. If you look closely at this figure, you see a dark shaded little part, which is zoomed out. This is the upper part here. This is the so-called representative volume element, abbreviated as RVE. And a condition for multiscale analysis is that the length, the characteristic length, lowercase l, is very much smaller than uppercase L. Exactly, it must be at least 1 order of magnitude than L and lambda. Then you see here so-called inclusions. Yes, for example, the aggregates in concrete. They are modeled, for example, by little spheres. And the characteristic length of these spheres is denoted as lowercase d, and lowercase d must in turn be at least 1 order of magnitude smaller than lowercase l. If these conditions apply, we can compute a characteristic quantity for mechanical analysis, the stiffness tensor of the mechanically equivalent material, denoted as C-OM. Well, ladies and gentlemen, concrete is a porous material. Its strength and stiffness develop in the course of hydration. These are time-dependent material properties. Frequently transport of possibly aggressive fluids needs to be considered. The essential processes must be considered at their levels of action. And this results in the solution of a multi-scale, multi-field problem. The example I'm showing here deals with thermo-chemomechanical couplings. You see 3 fields: the red one, temperature; the yellow one, chemistry; and the blue one, mechanics. And you also observe there are interactions between the two. For example, hydration. Hydration of young concrete results in a temperature increase in the structure and consequently in an improvement of the mechanical properties of concrete. On the other hand, the temperature has an influence on the chemical reaction between the cement and water, and the strains due to changes of temperature result in additional mechanical loading of the structure. What is shown on this slide is a typical multi-scale model for concrete consisting of 4 different scales. The finest one is the so-called CSH, calcium silicate hydride scale. The characteristic length of the RVE ranges from 10 to the -8 to 10 to the -6 meters, and typical inclusions are low density and high density CSH. The next higher scale is the cement paste scale, with L ranging from 10 to the -6 to 10 to -4, and typical inclusions gypsum, monosulfate, portlandite, adringite. Then comes the mortar scale, and finally the macro scale. What needs to be considered is the type of concrete, progressive hydration for young concrete, and dehydration for concrete under fire load. Hydration results in a change of the material composition of the young concrete, which is considered at the hydrate and the clinker scale respectively, and at the cement-based scale. The macroscopic material properties are determined by means of homogenization techniques on the basis of the morphology of the individual ingredients and of the mechanical properties on the three lower levels of consideration. Ladies and gentlemen, I'm reporting now about two sub-projects of the aforementioned project, Bridging the Gap by means of multiscale analysis. The title of the first one reads as Microstructural Analysis of Impact and Blast Loading of Tunnel Linings. In charge of this sub-project was Dr. Technik Eva Binder, presently a postdoctoral fellow at Linnaeus University, Växjö, Sweden, about to finish her Chinese PhD studies in the framework of a double-degree program of the Technical University of Vienna and Tongji University, Shanghai. The title of the second sub-project reads as Multiscale Analysis of Thermal Stresses in Cement Linings due to Sudden Temperature Changes. In charge of this project is Dr. Technik Hui Wang, PhD, Assistant Professor at Shanghai Jiaotong University. He has successfully completed both his Austrian and Chinese doctoral studies in the aforementioned double-degree program. Ladies and gentlemen, motivation for this research project is treatment of exceptional load cases in tunneling by means of multiscale analysis. Such exceptional load cases are traffic accidents, left figure, and explosions, high right figure, both resulting in high dynamic loading of concrete lines. The research question that is posed here reads as, can high dynamic strengthening be modeled by multiscale analysis? Let us have a look at the next figure. It gives experimental evidence that the strength increases with increasing loading rate. Take a look at this figure. It shows the so-called dynamic strength increase factor, which is equal to the ratio of the dynamic strength over the static strength as a function of the so-called strain rate. You see here experimental results obtained by many research groups from all over the world. What you can observe is that with increasing strain rates, irrespective of the large scatter of the results, the values of the DAF is increasing. It's particularly large in the high dynamic testing regime strain, larger than 1/2. Let me now say a few words about modeling of high dynamic strengthening in compression tests. Cracking is assumed to start when the quadrastatic strength is reached. In compression tests, and I'm restricting myself in this lecture to compression tests, crack propagation typically occurs in the loading direction, and what happens is actual splitting. Crack propagation takes place along nanoscopic interfaces. The speed of cracking is approximately equal to the Rayleigh wave speed, and the latter is approximately equal to the shear wave speed. Dynamic strengthening occurs during crack propagation, and the dynamic strength is reached when the first crack splits the specimen. Let us have a look at this figure. It shows 3 straight lines. What is illustrated here is the stress as a function of time on the assumption of a linear stress rate. The larger the stress rate, that means the larger the slope of this line, the larger the difference between the dynamic strength, F dün, and the static strength. Let's concentrate on the abscissa axis, on the 2 brackets below the abscissa axis. The green one shows the duration of loading up to the static load, and the black one, the duration of crack propagation. Well, the mathematical formulation of this model is comparatively simple. The dynamic strength is equal to the static strength plus a term that consists of a product of the stress rate and the duration of crack propagation. This formula contains the crack propagation length, L sub C, and I'll come back to this later on. The dynamic increase factor in which we are interested is then obtained by dividing F din over F star. It's a simple expression. It doesn't contain any fitted parameters, and high dynamic strengthness is proportional to L sub C. Well, unfortunately, there's an uncertainty regarding the crack propagation lengths in compression tests. The quantity L sub C actually depends on the location of crack initiation. And Dr. Binder considered two extreme scenarios. Extreme scenario one is characterized by the assumption that cracking starts at the surface of the specimen. We have one propagating crack tip from top to bottom, and the crack propagation length L sub C is equal to H. Extreme scenario 2 is based on the assumption that cracking starts at the center of the specimen. We have two crack tips, and the crack propagation length accordingly is equal to H over 2. I'm coming to validation of the hypothesis. Our analytical results are the black and the blue curve referring to the two aforementioned extreme scenarios. And the little rings show the experimental results. What is related, what is computed is the dependence of the dynamic strength increase factor on the strain rate. And you see that the degree of agreement is quite good. The same applies to mortar. Now coming to concrete, here you see only one curve. The reason for this being is that we fortunately have a photo of the mode of failure here. And it's obvious that failure starts in the middle of the specimen. So extreme scenario 2 applies. Results again are very good. And the same can be said about the results for concrete tested by Howe et al. Ladies and gentlemen, I'm coming now to multiscale analysis for stiffness and strength of concrete of the Hongkong-Zhuhai-Macao Bridge. We have 4 scales: hyded foam, cement paste, concrete, and reinforced concrete. Let's concentrate on the left figure. It shows the modulus of elasticity, which is a typical mechanical quantity for measuring the stiffness. Our result is the black curve. The little rings are experimental data, and the little crosses refer to hardening steps. They refer to different quasi-static strength values, and these quasi-static strength values are related to the time lapse between casting of concrete and the time of observation. I'm not commenting on the shear modulus relationship to the quasi-static strength. It's similar, and unfortunately, we don't have any experimental values for that. Well, let us have a look at this figure. What we are interested in is to study the influence of concrete hardening on the high dynamic strength. The respective formula is given here. The second term is approximately constant. Let us concentrate on the right figure. It shows the dynamic strength as a function of the strain rate for 4 different values of static strength. That means for 4 different distances in time from the casting of concrete. And expectedly, with increasing static strength, the dynamic strength is increasing. Ladies and gentlemen, so far for the first sub-project. I'm coming to the second sub-project. The title, I've said it before, let me repeat it: Multiscale analysis of thermal stresses in concrete linings due to sudden temperature changes. Motivation for the sub-project was to understand the reasons for thermal degradation, the consequences of thermal degradation on the concrete tunnel structures. Have a look at the figure. It shows the Mont Blanc tunnel after the big fire in 1999. There are 2 kinds of high temperature degradation mechanisms. One is thermal stresses caused, for example, by macrostructural constraints, or alternatively by microstructural constraints due to a mismatch of thermal expansion coefficients of cement paste and aggregate. The other reason is thermal decomposition by means of dehydration and decarbonation. Well, we are interested, as I said before, in the mismatch, the consequences of the mismatch of thermal expansion coefficients of the cement-based and aggregate. The table here shows different values of the thermal expansion coefficients for different types of rock and minerals. The figure shows the thermal expansion coefficient as a function of the relative humidity, both for the aggregates, the red dashed line, practically independent of the relative humidity, but the situation is strikingly different for the cement base. We see a strong dependence on the relative humidity. Well, I cannot save you from a little bit of mathematics. I'm describing now briefly the multiscale model for concrete. What you see here is a representative volume element. The pink part refers to the cement base, and the little spheres actually should be to the aggregates. Three quantities are relevant: the volume fractions, the thermal expansion coefficients, and the elastic stiffness tensor. The analysis starts with quantifying the microscopic behavior, the phase eigenstrains and the phase eigenstresses. You see here, obviously, the temperature difference, delta T plays a role, and the thermal expansion coefficients for the two phases. Once these quantities have been computed, we can determine the macroscopic behavior. The formula is relatively involved. It contains the homogenized stiffness. Keep in mind, we are homogenizing material that is originally heterogeneous, and the homogenized eigenstress. And this allows us to compute by means of bottom-up homogenization of thermal expansion coefficients, allows us to obtain a very nice formula for computation of the thermal expansion coefficient of the homogenized material. Take a look at the table here. It gives the input in red color, both for the aggregate and the cement base, for several quantities: modulus of elasticity, shear modulus, thermal expansion coefficient. And it also gives the results in green color. And if you take a look, for example, at the third column, you see here Young's modulus. That's another name of the modulus of elasticity. For the aggregate 60, and for the cement base 2234. And the value we obtain from multiscale analysis is somewhere in the middle, 43.30. These green values are then input for macroscopic thermomechanical analysis. Well, let us. Okay, Dr. Hui Wang analyzed a macroscopic reinforced concrete beam. The cross section is shown here with the reinforcement in the beam as such. We considered thermal insulation on the side faces in order to be able to apply a very simple differential equation, the one-dimensional heat conduction equation. You find it in any textbook on thermal elasticity, with uppercase T denoting the temperature, lowercase t denoting the time, y denoting the vertical component of the cross-section, and A standing for the thermal diffusivity of concrete. Well, here you see a relatively complicated formula, but it is in fact not so complicated. You find it also in good textbook. What is interesting here is the relationship between this quantity, which contains the temperature, and the height of the beam. There are four different curves for four different instants of time. For the shortest instant of time, the dashed curve, obviously only the lowermost part of the cross-section of the beam close to the fire load is affected. Finally, at so-called stationary conditions, we have a straight line. Now, these temperature fields are used as input for finite element simulations. And Dr. Hui Wang analyzed two beams, a so-called simply supported beam and a clump supported beam, for a temperature difference of 100 degrees centigrade. And what he computed was the distribution of the axial normal stresses over the height of the two beams for four different time instants. What is interested here, take a look at the left figure, is the tensile stress in the lower part of the beam. That's rather unpleasant because you wouldn't realize it. These stresses are inside the beam, not on the upper and not on the lower surface. For a simply supported beam, for stationary conditions, we have no stresses. And this is illustrated by the vertical dashed dotted line. Ladies and gentlemen, this is a result also obtained by Dr. Fujima. It shows the three stress components, actual stress components. And what is very bad in this situation is a three-axial tensile stress combination, which is certainly not something that concrete likes. Ladies and gentlemen, let me summarize the conclusions drawn from the joint Austro-Chinese research project. The project has proved the added value of multiscale structural analysis. It has underlined the importance of both material tests and structural large-scale material experiments. And last but not least, it has enabled participation of highly qualified students from both Tongji University and the Technical University of Vienna in challenging research in the framework of their doctoral study. Ladies and gentlemen, I'm using the last minutes of my talk for saying a few words about the witnessed development of modern China. It started in 1981 when I worked as a UNIDO expert at the Zhengzhou Research Institute of Mechanical Engineering from September to December 1981. My task was instruction and guidance in computer-oriented stress analysis. The Research Institute was founded in 1971. Actually, it was established in the form of a transfer of a department of another research institute from Beijing to Zhengzhou. My accommodation was in an old guest house, built at the time of the close political relationship between the People's Republic of China and the former Soviet Union. This figure contains the title page of my report to the United Nations Industrial Development Organization of my work at this instance, which was very interesting, but unfortunately, there's no time to comment on that. Ladies and gentlemen, what was my first impression when coming to China? It was the airport, of course. And the airport was rather small, given the fact that China is the country with the largest population on Earth. So I was a little bit disappointed by the small size of this airport, but look at the airport now in 2019, and you can see there's a considerable change. Next, my first impression on Tiananmen Square. Well, similar is shown here on the left figure. Masses of cyclists, most cycles, no lights, almost no cars, only official cars. Look at the situation in 2018. Almost no bicycles, lots of cars, many of them by electric power, actually, powered electrically. My observation of the development of modern China, that would fill, of course, another lecture, in the framework was taking place in the framework of several research cooperations. From 81 to 85, cooperation with the Zhengzhou Research Institute of Mechanical Engineering, guiding a PhD student, and cooperation with guest scientists from Sweden at the Institute for Mechanics of Materials and Structures of the Technical University of Vienna. From 1989 to 1994, cooperation with the China Aeronautical Establishment, again, guidance of PhD students, guest lectures. Since 2005, cooperation, and a very fruitful cooperation, with the Department of Geotechnical Engineering of the College of Civil Engineering at Tongji University, Shanghai, guiding PhD students, joint conferences since 2012, holding a chair professorship, and since from 2015 to 2020 involved in a joint research project. And since 2015, I'm also involved in participation in specific activities of the Chinese Academy of Engineering, co-editing scientific journals, in being involved in joint symposia with other academies. Well, just on June 4, I'll be involved in a defense of the thesis of a Chinese student who studied for 3 semesters in Vienna, completing his studies in China now, and will complete his studies in Vienna in fall of this year. The last few slides. My place of work in China now is Shanghai. How did it look like when I came to China? Well, the left photo shows this, and you still see the dominating colonial style on the famous pond. How does the southern side of the Huangpu River look like now? Well, you see the many new buildings, among them the impressive Shanghai Tower. When I came to China, it took me a whole night to go from Beijing to Zhengzhou. The average speed of the train was 30 to 40 kilometers per hour. Now, when I go from Shanghai to Beijing, I have to consider whether to go by plane or to go by train, because the high-speed train makes 350 kilometers per hour. Ladies and gentlemen, I'm coming to the epilogue. The Hongkong-Zhuhai-Macao Bridge is an outstanding symbol of the modern development of China, not only in a scientific and an engineering sense, but also in a figurative sense. I would like to make a couple of acknowledgements. I'd like to appreciate support by Dr. Qielong Zhang, Assistant Research Fellow from Tongji University, Shanghai, China, Dr. Eva Binder, Postdoctoral Fellow at Linnaeus University in Växjö, Sweden, Dr. Hui Wang, Assistant Professor at Shanghai Jiaotong University, China, in the form of providing material for this lecture, and by MS Gabriel Jostowski in the form of preparation of the PowerPoint presentation of this lecture. This is all gratefully acknowledged, and I don't want to forget to mention MS Martina Pöll, who also helped me with the PowerPoint presentation. Ladies and gentlemen, the final slide shows our research team. In the middle, Professor Yuan Jung from the College of Civil Engineering, the Department of Geotechnical Engineering. To the left, the 2 Chinese students I've mentioned just before, Dr. Qielong Zhang and Dr. Hui Wang. In the background, Professor Bernhard Binder from my institute, 2 Austrian students, Dr. Thomas Schlappal and Dr. Eva Binder, and on the right, it's me. Well, thank you very much for your attention. And I apologize if I was a little bit longer. Hopefully not too long.
No problem. Thank you very much, Professor Mang. It's a really interesting presentation, especially the last part. The first part is very interesting for me because I'm a geotechnical engineer. But I think for all the audience, the second part about the witness of China is very interesting for them. And also it's very valuable for our forum today. It's your witness. And Professor Yuan said in the chat, thanks for 40 years of cooperation with China, Professor Mang, and especially your support to my group and Tongji University. Thank you.
My pleasure.
Do we have any questions from the audience?
Hello, Linjia, I have a question.
Yes.
Hello, Professor Mang. This is Jiao Longzhang speaking. I never heard any professor who collaborated with China for so long time, 40 years. So my question is that what's your motivation to carry out such a long-standing collaboration with China? What's your motivation?
This is very easy. I was fascinated from the very beginning, say, about the high spirit of the people I met in Zhengzhou. These were partially people who suffered in the Cultural Revolution. And I had the chance to help them, bring some of them over to Europe. Say, I realized, my wife, by the way, worked at the United Nations Industrial Development Organization. Because of my name, Mang, she was often confused to be Chinese. And so the possibility, say, to observe the dramatic improvement of the situation in the cities which I got to know. Of course, I didn't get to know many parts, motivated to carry on and with this cooperation, and particularly the cooperation with the geotechnical department of Tongji University, which goes on now for 16 years actually. And as I said, we are planning new activities, and let me hope that this cooperation, which has been beneficial to both sides, Chinese side and the Austrian side, will carry on. I hope for the best in this respect, and I would combine this hope with my best wishes on the occasion of this event, the 50 years anniversary of diplomatic relations between China and Austria. Science is important part of our life, and scientific relations between countries play a big role in the whole relationships. So let's hope that this can be extended and continue. Thank you very much.
Thank you. Thank you.